So we are solving logarithmic equations today. Oh, I think we jumped ahead and did an application problem. You know what? Let's just finish these application problems first, and then we'll come back to logarithmic. So we were working on exponential growth and decay. Totally going to have one on the final. We're using a equals a sub 0 times e to the k times t power, where a sub 0 is our initial amount. A is our amount after some number of time t. T is our time. K is our constant representing the growth or decay. If our k value is positive, our entity is growing, but if our k value is negative, then it is getting smaller. So the first one we did here had to do with population growth. Another really common application of exponential growth and decay has to do with half-life. Half-life is a concept that we discuss in chemistry. Half-life simply is the amount of time it takes for half of a substance to disappear, which is, well, why we call it half-life. The isotope plutonium-238 is used to make thermoelectric power sources for spacecraft. Now, because I know not everybody's taking chemistry, when it says isotope plutonium-238, plutonium is an element on the periodic table of elements, but there are like variations to these elements depending on if they have more or less neutrons, I think. So that 238 is irrelevant. It's just part of the name, plutonium-238. A spacecraft was launched with 2 kilograms of plutonium-238 if the half-life of plutonium-238 is 87.7 years. The first thing we want to do is write a function to model the quantity of plutonium left after t years. We'll round our k value to 5 decimal places, and then we'll use that equation that we come up with to answer the question in part B. So we're using the equation a equals a sub 0 times e to the kt power. We need to fill in numbers for a sub 0, and t, and then solve for k. So do we know any of those things? What information was given to us?
The amount and how many years?
Exactly. So the amount that was given, that was when it was launched. So that was the initial amount. I'm going to switch my a sub 0 and my a. I want my a sub 0 first. All right, so my initial amount was 2 kilograms. And then they told us the half-life is 87.7 years. So that means that half of my substance is going to disappear in 87.7 years. Well, A represents the amount we have left after however much time. So if we started with 2 kilograms, how much are we going to have left after 87.7 years? We're going to have half of it left because it's half-life. So that means that half of it disappears. So half times 2, our A is just 1. Now we have our a sub 0, and t that we can plug in our equation and solve for k. Does anybody have any questions about anything we've done so far? All right, let's plug it in and solve. 1 equals 2 times e to the k times 87.7 power. This is an exponential equation that we're solving because the variable we're solving for is located in the exponent. To start solving this, we need to isolate the exponential portion. So I'm going to divide both sides by 2, and I'm going to clean up that exponent at the same time. We get 1/2 is equal to e to the 87.7 k power. Now that the exponential is isolated, we can rewrite it in logarithmic form. Our exponential base is e, therefore, when we rewrite it, our logarithmic base should also be e. That's our natural log. We get the natural log of 1/2 is equal to 87.7 k. And then we'll divide to get our k value. And we are rounding to 5 decimal places. So that's going to give us k is equal to negative 0.00790. It's no surprise that our k value is negative because our amount is decreasing, it's decaying, it's disappearing. So we anticipate a negative k value here. I want to mention some calculator things here just because it came up with my class yesterday. Because these k values are very small numbers, some calculators are spitting out the answers in scientific notation, especially that like silver one. It's just I don't know if somebody has one, if they're experiencing this, they want to show it to the group. So if you're seeing something that looks like 7.9 times, and then it does like it might have a whole bunch of decimal places after it, and then it says E and then -4 or something like that. That's your calculator spitting it out in scientific notation. I'm sorry, it's usually a capital E, not to be confused with the exponential E. So if you're having any issues with that, let me know. Stick out around after class. I would encourage you to try to do all of these decimals in your calculator as we're going so that you don't end up not being able to use your calculator on the test. All right, we found our k value, but now we actually have to write the equation that we're going to be using, the one that models this. To write the equation, we simply plug the original amount and the k value that we just found into our equation. We end up with a equals 2 times e to the negative 0.00790 t power. Questions, anybody? All right, well, part B says that if 1.6 kilograms of plutonium-238 is needed to power the spacecraft's data transmitter, for how long after launch would scientists be able to receive data? We'll round our answer to the nearest tenth of a year. How would we figure out part B using the equation we came up with there in part A? What is that 1.6 that they just gave us? Well, if we look at our equations, we only got 2 spots to put it. We either can put it for A or we can put it for T. T is a time period, and A is the amount we have left after that time period. So 1.6, definitely an amount, it's going in for A. So we're going to have 1.6 equals 2 times e to the negative 0.00790 t power, and we want to solve for t. We'll follow our procedure for exponential equations since our variable's in the exponent. So let's isolate the exponential. We'll divide both sides by 2, giving us 0.8. Now that we have isolated the exponential, we want to rewrite it in logarithmic form. We'll be using log base e, which is our natural log. Natural log of 0.8 equals negative 0.00790t. And then the last thing to do to solve for t is we will divide. We want t rounded to the nearest tenth of a year. We're going to get 28.2. And this one is different than the last example that we did on Thursday last week, where we had to round up. See, here it said by which year. It was looking for a calendar year. So we had to automatically round up to the next year because we're talking calendar year. Here, they're not asking us for what year. They're just saying how many years. Therefore, we will not be rounding up. It's just 28.2 years. Questions, anybody? All right, let's try another one. The half-life for thorium-229 is 7,340 years. We want to know how long it will take for a sample of this substance to decay to 20% of its original amount. We'll be rounding our K value to 6 decimal places, and then our final answer to the nearest tenth of a year. Well, the first thing we need is our general equation for this half-life. We'll be using our exponential growth and decay model. A equals a sub 0 times e to the kt power. So we need to be able to plug in for a sub 0, and t so that we can solve for k. Of those three things, what was given to us?
Years and percent.
There's a year and there's a percent. So
There's
this first sentence here is really all they're giving us for figuring out our original equation. This is like the part A. And then the second sentence we're going to be using, this is the question that they're posing to us. So we will use that 20%, but not until we actually figure out what K is and write our equation. So really all they've given us is the time. They did not give us a specific original amount. With a half-life problem, when an original amount is not given, you're just going to choose one. And for now, I just need you to believe me, but then I'm going to show you what I'm going to give something to back it up in a couple minutes. So when an original amount is not given, we're just going to choose one. So let's just choose an amount for a sub 0. What would you like to choose? It is an amount, so we do have to have a positive number. It can't be negative, it can't be 0. Anybody have a positive number they prefer?
2.
Sounds good to me. So our original amount is 2. Since this is a half-life problem, A is how much is left after time t is gone by. Well, A is going to be half of a sub 0 again, just like the previous example. So we get 1. Now I'm going to plug it into this equation and solve. One is equal to 2 times e to the k times 7,340 power. We're going to solve this exponential. We'll start by isolating the exponential. So let's divide both sides by 2. And then I'm going to clean up that exponent as well. I'm going to pause right here for a second because I want to point something out to you. Because I said, oh, just choose a number. And that's like, how can I just make up a number? That seems crazy. Well, let me show you why we can do that. So say I had chosen something else. Say we chose our a sub 0, I don't know, to be 10. And then our a would be 5. So if we did that, and our t is the same, if we did that, we would have the equation 10, no, wrong way. We'd have 5 equals 10 times e to the k times 7,340 power. And since we're solving an exponential equation, the first thing we're going to do is isolate that exponential by dividing both sides by 10. And when we do that, we get 1/2. So you see, we end up right at the exact same equations. So you can choose whatever you want for your a sub 0. You just have to make sure that you cut it in half for your a when you're doing these half-life problems. All right, back to solving this. We're ready to rewrite it in logarithmic form. Natural log of 1/2 is equal to 7,340k. And then we'll divide by 7,340. We get k to be equal to negative 0.0000094. Any questions so far? All right, so now I need to write my equation that I'm actually going to use to answer my next question. Because an original amount was not given, we're not going to plug anything in for a sub 0. We're just going to leave it generic. So the equation that we're going to use to answer the question is going to be a equals a sub 0 times e to the negative 0.0000094 t power. Now it's time for the question. How long will it take for a sample of this substance to decay to 20% of its original amount? We're solving for t because it's saying how long, so that's a time. That means that we need a value for a and a sub 0 so that we can plug it in. Do they give us a specific a? No, they still haven't given us an a or an a sub 0, so we're just going to choose a sub 0 to be whatever we like. You can choose the same a sub 0. Usually when I have the choice of choosing a sub 0, I always choose 1. I'll show you why. We'll choose 1 this time. I'll show you why. They want to know how long it's going to take for this sample of the substance to decay to 20%. So that means we want 20% of the original. So to get our A, we're doing 20% times a sub 0. So that's 0.20 times 1. We're getting 0.2. We're ready to plug in and solve for t. So 0.2 equals 1 times e to the negative 0.000094 t power. The reason I like to choose a sub 0 to be 1 is because you'll notice, right, with this 1 here, I don't have to do that extra step of dividing both sides by whatever that number is, like we had to do up here. Since we chose 2, we had to isolate the exponential by dividing both sides by 2. If you choose your initial a to be 1, you know, it kind of just disappears and we don't have to divide. And if I can eliminate a step, then I eliminate the chance that I make a silly mistake. We're ready to go to rewrite it in logarithmic form. Natural log of 2 is negative 0.000094 t. And then we'll divide. Wants us to round to the nearest tenth of a year. So again, it's not asking us what year. So they're not looking for a calendar year. We just want how many years. We get t to be equal to 17,121.7 years. Questions? You will definitely be seeing a half-life problem on the final exam. A lot of you are taking Math 103 just to even get into chemistry. So it's really important that we do a chemistry application on the final exam. We ended up with an answer that was pretty big, but it kind of makes sense. Oh, the half-life is 7,340 years. So that means that we go down to 50%, 7,340 years. When we go another 7,340 years, half of that half disappears. So half of the half is 25%. So after 14,680 years, we're going to be down to 25%. Well, 20% is less than 25%. So I'm expecting that it's going to take longer than 2 half-lives to get below 25%. Another type of application I'd like to discuss is Newton's law of cooling. Newton's law of cooling discusses, so if you take a hot cookie sheet out of the oven, it's 350 degrees, and I set it on the counter in my kitchen that's 70 degrees, how long does it take for that aluminum pan to cool down so that I could actually touch it? So that's Newton's law of cooling. The temperature T of a heated object at time little t is given by T equals C plus T sub 0 minus C times e to the kT power, where C is the constant temperature of the surrounding medium, T sub 0 is the initial temperature of the heated object, and K is the negative constant that's associated with the cooling object. So it says that, so T is the time, not the initial time. T sub 0 is our initial temperature, so that's the hot cookie tray coming out of the oven. T is how hot it is after 5 minutes, 10 minutes, 20 minutes. C is the constant temperature of the surrounding medium. So if my kitchen's 70 degrees, that's the C value. They say it generically there, like constant temperature of surrounding medium is because things are cooled off in a variety of ways. It's not just necessarily left on the counter to cool. When they do glass blowing, they dunk it in water. Same thing with steel a lot when they're heating it up. Sometimes it's put in sand to cool it down. So that's why they're being generic there. This is a real life lesson. My son learned it the hard way one time, tried to smell some cookies on a cookie sheet and burnt his face on the cookie sheet real good. So, Newton's law of cooling, important to know. An object is heated to 100 degrees Celsius. It's left in a room to cool that has a temperature of 30 degrees Celsius. After 5 minutes, the temperature of the object is 80 degrees Celsius. We want to use Newton's law of cooling to find a model for the temperature of the object T after little t minutes. We'll round our K value to 5 decimal places. And then we'll use whatever we come up with in A to answer the questions in part B and part C. I'm going to do part A, all of us together, and then once we get the formula, I'll let you guys work on parts B and C. So starting with A, well, we need quite a bit of information. We're going to be solving for K in this formula up here. So that means I need to know what T, C, T sub 0, and little t are so that I can plug in. They gave us a bunch of information. Let's just figure out what it all is. An object is heated to 100 degrees Celsius. So what is that 100 degrees? Which variable is that?
Temperature.
Well, which temperature? The initial temperature or the temperature after a certain amount of time?
The initial.
The initial temperature. So that's our T sub 0. Then it's left in a room to cool that is 30 degrees. So what's our 30?
The constant temperature?
You got it. That's our C value. After 5 minutes, so that's definitely our little t, the temperature of the object has cooled down to 80 degrees Celsius. So what's the 80?
A big T.
The big T. So now we have everything except K, and we'll plug it into our equation and solve for K. So 80 equals 30 plus 100 minus 30 times E to the K times 5 power. I'm going to do some cleanup here. I'm going to subtract those numbers in the parentheses and fix my exponent. We get 80 equals 30 plus 70 times E to the 5K power. Now we want to solve for K. It's in the exponent, so we're following our steps for solving exponential equations. We'll start by isolating the exponential. So let's subtract 30 from both sides. And then we'll divide by 70. That simplifies nice, so I'd probably take it down to 5/7. If it didn't simplify nice, I'd just leave it. Now that we have the exponential isolated, we're ready to rewrite it in logarithmic form. This becomes the natural log of 5/7 equals 5K. And then we'll divide to get our K value. We get K to be equal to negative 0.06729. And we're ready to write our general equation. If you quickly read through our parts B and C, what's the temperature of the object after 20 minutes? When will the temperature of the object be 35 degrees? In those subsequent parts, they don't change the initial heat up temperature. They also don't change the temperature of the room that the object is cooling in. So our T sub 0 and our C are remaining. Therefore, we want to plug those numbers into our general equation as well as our K. So we're going to have T equals 30 plus 100 minus 30 times e to the negative 0.06729 t power. And I would take the extra step and clean this up and combine what we have inside the parentheses there. T equals 30 plus 70 times e to the negative 0.06729 t. That's the equation that models this cooling, and we'll be using this to answer parts B and C. Questions at all on getting the equation? All right, well, I'm going to put you guys in groups then to answer parts B and C. All right, so for part B, we were just plugging 20 into our formula for little t. And then what did we get for a temperature?
I got 48.22.
And that is a believable answer because it said in 5 minutes it cooled down to 80 degrees. So I'm expecting in 20 minutes that it's cooling down way more than 80 degrees. So I feel good about that. And then in part C, we had to plug 35 in for our big T and then solve for little t. So we want to know how long it's going to take for it to cool down to 35 degrees. Well, because 35 degrees is less than this 48 degrees we got in part B, I'm expecting that it's going to take a longer time than the time it took in part B, which was 20 minutes. So I'm expecting a T larger than 20 minutes. What did you guys get for your time?
39.22.
Great. Did anybody not get either of these answers? Each group seemed pretty good. I just want to make sure. Okay, great. I'm not doing the last example. I don't even know why this is in there. I should just take it out of the book. I hate it. I skip it most of the time. It's not really applicable to anything that you're going to like ever do. All right, so let's jump back and we've got 4 logarithmic equations to solve. I think logarithmic equations are a lot easier to solve than exponential equations because there are far fewer options on how the equations can look. Just like with the exponential equations, our logarithmic equations have a one-to-one property, and that is always my first choice to try to use the one-to-one property. Our one-to-one property says that if log base b of x equals log base b of y, then x equals y. So if you can rewrite it as 1 log equal to 1 log, those logs have the same base, then it forces their arguments to be equal to each other as well. The nice thing about logarithmic properties is that I know immediately, as soon as I look at the equation, whether or not I can use the one-to-one property. If every single term in the equation contains a log, we can use the one-to-one property. Now, it might not be ready to go yet, but we know that we'll be able to use it. To use the one-to-one property, we have to have 1 log equal to 1 log. Sometimes we'll have multiple logs on each side of the equation. So if that's the case, you want to combine logs on each side so that you do have 1 log equal to 1 log. And that's why we practiced combining logs earlier last week or the week before. So once you get it to 1 log equal to 1 log, we'll apply the one-to-one property and simply set the arguments equal to each other and then solve. If every term in the equation does not have a log, well, then we're not going to be able to use the one-to-one property, and instead we're going to have to rewrite it in exponential form. In order to rewrite it in exponential form, we need to have a single log equal to a constant. So again, it may not be ready to go. We might have to combine logs to accomplish one log equal to a constant. Once we get it there, we'll rewrite it in exponential form and solve the equation. A very important thing is, since we know that the domain of logarithmic functions is restricted to 0 to infinity, we know that the argument of a log has to be positive. You're going to have to quick check your solutions in the original equation and just make sure that when you plug it into the original arguments, you always get a positive number. If you don't, you're going to have to throw it out. Let's solve. Natural log of 3x minus 10 equals the natural log of x plus the natural log of x minus 4. Am I going to be able to use the one-to-one property? Absolutely. Every single term contains a log, right? I don't have like a +5 over here on the end. So every term has a log. I can use the one-to-one property. It's not quite ready to go yet, though, for one-to-one property, because we need one log equal to one log. So we need to combine these two logs on the right side. These logs are being added together, so how do we combine them? We need to multiply the arguments together. Now that we have one log equal to one log, we can set the arguments equal to each other by the one-to-one property. So 3x minus 10 is going to be equal to x times x minus 4. And we solve. We'll start by distributing. We see this equation is quadratic, so I'm going to set it equal to 0 and factor it or use quadratic formula. I'm moving everything to the right to keep my leading coefficient positive. X squared minus 7x plus 10 factors nicely. X minus 5 times x minus 2. Zero product property. We get x to be equal to 5 and x to be equal to 2. Oh, we need to quick check our solutions in the original. So we'll just take them and plug them into the original argument. Make sure that we get a positive. If we don't, we got to throw it out. So if we plug 5 into these three arguments and clean it up, do we always get a positive? Sure do. But then we'll do the same thing and plug 2 in. Notice that when I plug 2, 3 times 2 minus 10, I'm getting -4. So I'm going to have to throw this out. Make some negative argument in our original equation. Questions? Let's solve log base 4 of 5x minus 13 equals 1 plus log base 4 of x minus 2. I would start by trying to use the one-to-one property. Are we going to be able to use it this time?
No.
No, because we have a term right here that does not contain a log. So that means that we're going to have to write it in exponential form. But it's not ready to go for exponential form. I need one log equal to a constant. So we need to get all our logs together. All my constants are already on the right, so I'm going to move this other log to the left. This is a log base 4 of 5x minus 13 minus log base 4 of x minus 2 equals 1. We've got the logs on the same side, so now we can combine them. How do we combine them when it's subtraction?
Division.
We're going to divide the arguments. And now we're ready to rewrite it in exponential form. Our exponential rewrite is going to be 4 to the first equals 5x minus 13 over x minus 2. That gives us 4 equals 5x minus 13 over x minus 2. We have a rational equation, so we're going to cross multiply to solve. That's going to give us 4 times x minus 2 equals 1 times 5x minus 13. 4x minus 8 equals 5x minus 13. Moving our x's to the right and our constants to the left, we get x equal to 5. But remember, we always have to check our answers in our original argument. Be sure that when you plug it in, you only get a positive. Does 5 work? Sure does.
Yes.
Questions, anybody? Let's solve 2 log base 3 of x minus 1 plus 12 equals 5 log base 3 of x minus 1. Are we going to be able to use the one-to-one property?
No.
No, this plus 12, right, doesn't have a log with it. So I know I'm not going to be able to use the one-to-one property. I need to get all my logs together and then rewrite it in exponential form. So I'm going to subtract this one over this way. We're going to get 12 equals 5 times log base 3 of x minus 1 minus 2 times log base 3 of x minus 1. There's something different that's occurring here than any problem that we've seen in this whole log chapter. What do you notice about these logs?
Their arguments are the same.
Not only do they have the same base, but their arguments are the same. We haven't had that in any of them. We scroll back and look, or even when we were practicing combining and tearing apart logs before, they never had the same base. I'm sorry, the same argument. So when a log has the exact same base and the exact same argument, that means that we have like logs. Well, what can you do with things that are like?
Combine them.
Combine them. So if I got 5 of these logs minus 2 of those logs, I end up with 3 of those logs. So this becomes 3 times log base 3 of x minus 1. Now, yes, we could have combined these a different way. You could have taken the coefficient, made it an exponent on both of them, then combined them by dividing the arguments, but you would have ended up with something that's much worse to deal with. We'd end up with like some kind of cubic. And same thing, even at this point where we are now, we need to get the log all by itself. So we got to deal with this 3. We do have the option of making that 3 an exponent, but then once we get it out of logarithmic form, we're going to end up with a cubic, and cubics are a lot harder to work with than things that are not cubic. So what could we do with that to get rid of that 3 instead of making it an exponent?
Divide both sides by 3.
We can just divide both sides by 3. And that's going to make our life a whole lot easier than having some kind of cubic equation to deal with. We get 4 equals log base 3 of x minus 1. Now that the log is isolated, we can rewrite it in exponential form. 3 to the 4th equals x minus 1. 3 to the 4th is 81. Therefore, x is equal to 82. Let's make sure that this answer works out, right? We got to quick check it in the original, make sure we don't get an argument that's anything other than positive. So if we take 82 and plug it into our original arguments, do we get a positive?
Yes.
Yep. So our answer is good. Questions, anybody? All right, last question for Math 103. Usually we do a drum roll when we're in class because it's exciting. I know this class is not easy and you guys made it to the end. I'm proud of you. So here we go, last question. We're asked to find the x-intercept of this log function, f of x equals 5 times log base 4 of x plus 3 minus 20. So how do we find the x-intercept of anything ever in our lives?
Set y to 0.
We let y be equal to 0. So we're going to let y be equal to 0 and solve for x. All right, I'm going to let you guys work on this. Our last collaboration of the year. All right, so it sounded like everybody was doing pretty good. I got an answer of 253. Anybody, any questions? Of course, since it was an x-intercept, we rewrote it as an ordered pair. Anybody, questions at all? Well, congratulations, you've made it to the end of Math 103.